Section 12.6, Solving Equilibrium Problems. You're going to have to solve equilibrium problems both on your exam and for homework. It's a pretty simple 7-step process that we're going to go through, develop a problem-solving strategy so that you can figure out how to do the problems that we're going to ask you to do to show that you know how to do equilibrium problems. So, number 1. Write out the balanced equation for the reaction. You're going to need the balanced equation so that you get that K constant. You need to know what your products are. You need to know what your reactants are. Write out that equilibrium expression using the laws of mass action, right? Products over reactants raised to the stoichiometric coefficients from the balanced chemical equations. Number 3, list the initial concentration. So go through, start setting up that ice table with the things that you know. Number 4, calculate Q. So if you're given some initial conditions, you need to find out if Q is going to be bigger than K, in which case you're going to go backwards and reconsume your products to form reactants, or if Q is smaller than K, in which case you're moving forwards and going to figure out that you're going to add to your products, take away from your reactants. 5, you're going to define the change needed to reach equilibrium. That's your minus X and plus X part. It's going to follow along with that balanced chemical equation you wrote down in step number 1. And define the equilibrium concentrations by applying the change to the initial concentrations. 6, you're going to substitute the equilibrium concentrations into the equilibrium expressions and solve for the unknown. And then 7, you're going to check your calculated equilibrium concentrations by making sure they give the correct value of K. On an exam, if you've got time to do this, great, do it. It's going to tell you whether or not you got that answer right. On the other hand, if you don't have time, that's the step you're going to skip, right? If you don't get the right value for K, plugging it back in, let us know that that's not the right value and that something wrong happened. Let's do a quick concept check. I've got a 2-mole sample of ammonia that's introduced into a 1-liter container. At a certain temperature, the ammonia partially dissociates according to the following equation, where our NH3 breaks down into nitrogen gas and hydrogen gas, and at equilibrium, 1 mole of the ammonia remains. So we're going to set up our initial balanced chemical equation, check, right? We're going to calculate the value for K. Right. This is very much like what we did in class on our worksheet. So just double check. You should end up with a value of K of 1.69. Another concept check. We've got a 1-mole sample of N2O2 gas placed in a 10-liter vessel and is allowed to reach equilibrium according to the reaction. We've got N2O2 giving us 2 NO2s, and we've got a K value that is given for us. We want to calculate the concentrations of the N2O4 and the NO2 gas. All right, so we're going to set it up. How we're going to do that, we're going to set up our ice table. We first got to take this 1 mole in 10 liters and make sure that we get the right concentration here in moles per liter. This should be a Kc. When we go through and do the math, pause, come back, work it out. Okay. Our concentration of N2O4 should be 0.097 molar when we're done. And our concentration of NO2 should be 6.32 times 10 to the minus 3rd molar. You ask yourself, does that make sense? And you look at this value of K, and this value of K is small. So of the two, which is it going to favor, the products or the reactants? Well, it's going to favor the reactants. I'm not going to get a lot of products because my K is a ratio of products to reactants. Let's calculate equilibrium from pressure. So we got gaseous hydrogen iodide. It's synthesized from hydrogen gas and iodine vapor at a temperature where the equilibrium constant is 1 times 10 to the 2. So that should be heavily favoring the products. Suppose that our HI at 5 times 10 to the minus 1 atm, H2 is at 1 times 10 to the minus 2 atm, and our I2 at 5 times 10 to the minus 3 atm are all mixed together in a 5-liter flask. We want to calculate the equilibrium pressures of all the species. So we're going to do a Kp. Right, we're going to find what this equilibrium pressure of all of our species are. Right, we've been given a Kp, we've been given some concentrations. How is it going to go? Right, so step number 1, we're going to write out the balanced chemical equation. H2 plus I2 gives us 2HI gas. Our equilibrium expression is going to be our products, HI, and we're going to square that over the pressure of the H2 and the I2. And again, we're using pressures as a stand-in for moles because pressures can be a stand-in for concentration. And we know that our value for K is going to be 1 times 10 to the 2. If our initial pressures are as given, 5 times 10 to the minus 1, 1 times 10 to the minus 2, and 5 times 10 to the minus 3, we're going to write our Q expression, plugging in our hydrogen iodide, hydrogen gas, and iodine pressures, making sure this guy's squared. Right? So we get 5 times 10 to the minus 1 squared divided by 1 times 10 to the minus 2 divided by 5 times 10 to the minus 3. And we see that Q is 5 times 10 to the third. And since Q is way, way bigger than K, we're going to have to shift our equilibrium. Right? We know that we're going to form our products back from our reactants because Q is very large. So it's going to shift to the left to reach equilibrium. So it is valid for us to use pressures for a gas phase system at a constant temperature and a volume because in this case the pressure is directly proportional to the number of moles. So our pressure is proportional to the moles times RT over V, and that's going to be a constant if your temperature and volume are constant. The change needed to achieve equilibrium can be represented in terms of pressures. So we'll set up an ice table where we've got our balanced chemical equation up at the top. Right? We know our initial concentrations of our three species, of our H2, our I2, and our hydrogen iodide. We know that we're going to put in a positive X here, and a positive X here, and a minus 2X here. So we're going to assume that it's going to take away from our product and backform some of these reactants because it's shifting to the left. And at equilibrium, we're just going to add up the I line and the C line together. So it's 1 times 10 to the 2 plus X, and 5 times 10 to the third plus X, and 5 times 10 to the minus 1 minus 2X. Where is this 2 coming from? From the stoichiometric coefficient over here. So every time I make an I2 or I make a hydrogen, I'm going to use up 2 HIs to do that. I'm going to find the value of Kp by substituting in the values into the equilibrium expression. So we've got our products over reactants formula again, but now we're putting in the new equilibrium values, including the x's. Right, so we got 5 times 10 to the minus 1 minus 2x squared over 1 times 10 to the minus 2 plus x times 5 times 10 to the minus 3 plus x. We're going to multiply and collect the terms to yield a quadratic equation, where a is 9.6 times 10 to the 1, b is 3.5, and c is minus 2.45 times 10 to the minus 1. We're going to set that all equal to 0, plug it into the quadratic formula, and the correct value for x comes out as 3.55 times 10 to the minus 2 atmospheres. All right, so please note that this quadratic formula is not on the test, all right? It's not on that formula sheet. So if you need it, you're going to have to memorize it. Right? There's a nice little mnemonic song out there that you can use. If you've got a calculator with a solver in it, you don't need to worry about it. But if you don't know it and you don't have a calculator with a solver, you're going to want to know that. But the equilibrium pressures can now be calculated from the expressions involving x. So we had 5 times 10 to the minus 1 as our initial pressure for our HI. We're going to subtract 2x, plugging in the particular value for x that we just calculated, and we end up with 4.29 times 10 to the minus 1 atmospheres as the pressure of the HI. Our hydrogen gas, we're going to do 1 times 10 to the minus 2 atmospheres plus 1x, or backforming that hydrogen, making a little bit more, 4.5 times 10 to the minus 2 atmospheres. And our iodine pressure is going to be 5 times 10 to the minus 3 atmospheres plus 3.55 times 10 to the minus 2 atmospheres, giving us 4.05 times 10 to the minus 2 atmospheres. The following equation agrees with our value of K, 1 times 10 to the 2, so the calculated equilibrium concentrations are correct. When the equilibrium constant is very small, right, this is our 5% rule. So these are some approximations. They're probably going to help you out. Right? So maybe we don't have to solve that quadratic. If we don't have to solve a quadratic or a higher order equation, that is a great thing. So when the equilibrium constant is very, very small, The position of the equilibrium favors the reactants. And if you've got a very large initial concentration of reactants, the reactant concentration is not going to change significantly when it reaches equilibrium. So it's like, oh, hey, I'm the bank, and I got $1 million, and all of a sudden I lose $4.50, right? The bank does not know that it lost $4.50. Right? Its relative worth is unchanged. So we can make the simplifying assumption that that change is going to be very, very small compared to the initial concentration. And that's going to let us simplify our equations by a lot. So if our equilibrium concentration is going to be equal to our initial concentration minus some small change, and this small change is insignificant, it's basically the same amount. So our initial and our equilibrium concentrations will be the same, meaning that the equilibrium concentration of the reactant is the same as the initial concentration. If the approximate value of X is less than 5%, that's just an arbitrary threshold. We're going to say 5% of the initial concentration, our approximation is valid. So our approximate X divided by our initial concentration times 100 is going to be about 5%. So let's review the steps, right? Preliminary setup. 1, write out the balanced equation. 2, write out the reaction quotient. 3, convert all of the amounts into the correct units, whether that's molarity, moles per liter for a Kc, or in atmospheres ATM if we're doing a Kp. Then we're going to work on our reaction table, our ice table. Right? When a reaction direction is not known, compare Q with K. 5, build that ice table. Check the sign of X, the change in the quantity. Make sure you're taking away from the right part and adding to the correct part. And that you're going to need to check with step 4, right? Making sure that you're going the right way. Solve for X and our equilibrium quantities. 6, substitute the quantities into Q. So combine your I and your C lines to give you your equilibrium lines. Simplify the math. Assume that X is negligible in the denominator. So all of our small changes on our initial concentrations, we're going to drop those. If you're squaring it, we're probably going to keep that X. Okay? So we're going to say that our initial concentration minus X is going to be about equal to our equilibrium concentration. So we'll say those two are unchanged. And then we're going to solve for X. And then our equilibrium quantities. Double check that the assumption is justified, less than a 5% error. If not, you're going to have to solve that quadratic. And then check to see that the calculated values give you the known values for K.